There we go. Okay, so we'll look at. So let's see. I guess let's talk about the reading thing for the homework here. So we're going to be on chapter 2, looking at instructions, and we're going to start we started talking about it a little bit last time. We're going to start talking about the binary side of things for the last half hour today. Let's see. So there is 23 sections in here.
20.
No, I get it. Some of these are, so really it's 21.
That quote, though, is a winner.
Which one?
Right below the
I speak
introduction.
Spanish to God, Italian to women, French to men, and German to my horse.
See? You didn't like this book.
I didn't have a problem with the readings. It's just the question.
The questions, stereo
That's when he's
instruction.
getting conversational. That's the interesting part.
Exactly. You know, this could actually be somewhat interesting. I'm going to look at this here real quick. This Mips Simulator.
Is that what you're looking for?
Yeah, but I really don't want to. I want Mips to be like the sample thing from the book. I want to look at Intel stuff for homework assignments. Yeah, I'll figure it out. Yeah, so like here, real stuff, x86 instructions. So I really want to deal with this stuff, these registers, EAX, and all that stuff. Okay. So we'll probably go through.
It sounds like a personal problem.
Look at the exercises here.
This part is real.
You just get this in your leg.
Couldn't even use them. This song was just sitting there freaking out like it's okay. I've done it before.
It's always terrifying when you like sleep on your arm and you wake up and you can't feel it
yeah.
at all.
Then I'm trying to lift it up, and then you lift it up.
Hey, Ema,
Yeah.
you try that at 350 pounds. You don't have an arm.
And then the worst part is you try to lift it up, and then you get to here, and it instantly hits you in the face.
It's like, did you see the video of from the Paralympics? Like a dude who like won an archery tournament, he's got no arms.
What he did, like with his teeth or something?
No, with his
Feet?
leg,
Oh, his feet.
Oh,
Okay.
So he won gold. And you see like the dude putting the medal on him, he goes to shake his hand. He's just like crap.
Yeah, some of the Paralympic athletes are kind of amazing. What I was watching the swimming, and you know, like this one lady, I think she got like the bronze. She was missing an arm, and the other arm wasn't fully developed. She was a swimmer, and I mean,
Is it?
I don't have a real great reference for like speed, but the impression I got was, I mean, I'm a pretty fast swimmer. I used to be on like swim team when I was younger, so I'm a pretty fast swimmer, but I got the impression that she would beat me by a lot in swimming.
Is it bad to surmise that maybe it's like, you know, maybe the winners had slightly more in terms of limbs, or?
But that wasn't, what I'm saying is that wasn't always the case.
Okay.
Yeah, I mean, it seemed like in swimming, a pretty high percentage of the athletes were in wheelchairs, which kind of makes sense because they would be more free to do things in water than they would be with gravity taking effect. But I mean, this lady had missing a full arm, and the other arm wasn't really doing much, and she got the bronze. And it wasn't that everybody was just slow, like doggy paddling. I mean, she was basically like a motorboat kicking, and she just used the one arm. She had a motion with it, but it was kind of to keep her level almost. I mean, they were fast. It's pretty shocking to me, actually.
So what do you do now? You just kind of float.
No, I mean I can swim. I can swim pretty quickly, but I mean it's still. I mean, I think it has less to do with me not being able, like my arms can move fast and stuff, but I mean I'm dealing with quite a bit of body drag. I haven't been able to fit into my speed suit in a little bit. I have to call every time I want to get into that thing. I have to call the fire department to bring over the jaws of life.
Spread it, and now I step in.
We got 11 cans of spray Pam just to get me into that thing.
WD-40.
Oh, here's another story. This was after I broke my back when I was still in college, and
Right after.
a couple of years I had already got big. I mean, I got big pretty quick.
Started the eating thing. Right?
Well, I'd already was eating big, but when you're playing 7 hours of tennis a day, it doesn't matter.
Okay, I guess.
So now imagine you're eating as much and then a little bit more because you're depressed, but not doing any exercise. Right?
I don't know.
What happened?
He's like, why is this funny?
Oh,
You
what-
said you were depressed.
Like
and
a
everyone
little bit
laughed.
more.
Oh, well, I mean, you know, like anybody else, if you get injured or something, you can't do something you used to do. It's depressing, right?
Yeah.
Yeah.
I think it's also because we know him.
Yeah. But the point is, so I had already gotten big, and my buddy and I, we were out, we went to some park or something, and I don't even remember exactly how this went down. There may have been some alcohol and stuff involved, but I was, you know how they have those the tire swings? Yeah, I'm stuck in one. Okay, so long story short, I'm stuck in a tire swing, and they have to butter me out of it. They're melting butter and like spreading it. Oh yeah.
Wait, you have to hear that story.
Yeah, I'm so. I just occurred to me that's never really come up.
Is this where your like obsession with butter has come out of? Or it's like seriously, oh, I gotta get some more of that.
Well, but really, where you need to kind of. So this is one of those tire things that like tied to a tree, right?
Yeah.
Okay, so we're not by the dorms. Dorms are where the butter is. Yeah.
So you're sitting.
So I'm tied to a tree. So you have a fat guy. You have a fat guy stuck in a tire, tied to a tree. His friends are bringing him offerings of butter. And they're smearing butter all over his body.
So what were the people that were passing by thinking?
Well, it really wasn't on like a direct path. I mean, there were people that would have seen it, but it wasn't like you had like lots of people coming by. So, like here on campus, think of it like if it was maybe sort of across the street, like back by the tennis courts.
Okay.
You know, not on the beaten path, but somebody might see it. Yeah, I probably had to explain it to maybe 5 or 6 people or something like that.
I could just imagine your explanations. Like you get creative with like, my friends tend to lose me, so they just don't go anywhere. Stay tied to this tree.
Do any of you guys have any spray lubricant? Just say it like in the creepiest way possible.
Almost like Sean Connery.
But it was actually surprising how well butter worked.
So
That thing came right off. I was like, ay. Yeah, officially hit rock bottom at this point. So it's the only way to go from here. There's no roads back from here. Okay.
That voice, Mike, I think you might have a problem. So was it at like the point where you could were you able to situate yourself where you could like stand up and just like your
No, it like
to the
sucked.
tree?
I was like at a weird angle, so like my ribs were bruised.
Ooh.
Yeah, it sucked.
you're sitting there like
It's
this,
like-
I can't move.
were you face down or up?
Face down.
Okay, so you're just like.
Yeah, kind of like hanging, and like my knees were sort of kind of on the ground.
Okay.
But like to stand up, I was like in a weird position, like I would get stuck trying to stand.
Ooh.
So your stomach
Was stuck inside of the tube. Yeah, there was at least a minimum of one fat roll inside the tube.
See, at that point, it almost looks like depressing. Like, look at that fat child there.
So there's not a whole lot to say.
I walked by and he just had this look on his face like, I've lost.
What happened to Gracie one time? My cat's dead now, but it was my fat cat. She was upstairs in my wife's office, and she was, I don't know, clawing at one of like the cat tree things or something, and she got her claw stuck in it and sat there for like 5 or 6 minutes trying to get out. Decided it wasn't coming out. Laid over there and just decided this is now my life.
There's a subreddit for that now. It's called This Is My Life Now.
Yeah.
It's just animals and people. With
Just gave up. So she's just laying there with her paw there. Like, my wife had to bring her food and stuff until I got home. Because my cat liked my wife. My cat was mean, but loved me, like never bit me, but bit everybody else. So she didn't want to like do too much.
He's not joking. Like,
Yeah, she was evil.
I would like get feet from this thing. I'd get this thing.
So she didn't want to get too close to her mouth because Gracie would have bit her bad.
I mean, she was hooked to a thing. I mean, there's probably like a certain reach that she could have gotten to take advantage of the situation.
Yeah, so when I came home, I had to get her detached. It was another day. It was several years ago that Gracie had Tabby cornered in her office upstairs. Tabby had to shut the door. So Gracie was on some meds and she wasn't reacting right to it or something, and she was pretty aggressive.
Your cats were like half feral though.
Yeah,
They were part lynx.
Gracie was fine when I got there.
Right?
I picked her up and just carried her downstairs.
They're all all your cats were part.
Yeah, they were 25% lynx. Well, now they're dead, but they were 25% lynx. All right. So I think I have a decent plan for the reading assignment, the homework assignment. So I'll write it up. But I think what I'll have you do is I'll have you read the sections 2.1 through 2.3. So pretty small section. And then do homework, the problems from the end of the chapter 2.1 through 2.7, which only are dealing with questions from those 3 little sections. Okay? I think that'll be a good blend of not having to cover too much material for answering the questions, but still give you work on the questions. Sound fair? All right, and I'll put that in an assignment, but just so you can have a game plan ahead of time. All right, so let's look at some binary stuff to finish the night.
Topic of this week's paper.
I do, but I'm not going to tell you yet because it's going to be the binary 2's complement stuff.
Oh, okay.
So 2's complement related. All right, so we want to talk about binary number representation. All right, so when we talk about binary, we're talking about zeros and ones. And some of this should be review for a lot of you, so I'm going to kind of go through this hopefully pretty briskly. But the question I would kind of ask as a global question is why do we want to represent stuff in binary? Our short answer should be that, well, it's because that's what computers understand. We've already referenced this idea of registers and things like that, and a register is going to hold, if you have an 8-bit register, it's going to hold 8 bits, 8 zeros and 1s. So having this number system in common with a computer is going to benefit us. All right, so when we represent numbers in binary, what we start doing is we start losing some of the things we're used to as humans working with base 10. So, we like decimal numbers, base 10 numbers, 10 fingers, 10 toes, blah, blah, blah. So we are quite comfortable working with positive and negative values of various sizes. Do all of us feel like if I give you any size number and told you to add to it any other size number, we could pull it off one way or another? You know, you might say, if some ridiculous size number, you might say, well, why would I ever do that? But you could still do it, right? Adding numbers is a process. It's not a memorization thing, right? All right, so same thing is true with binary, same thing is true with hexadecimal, and the process for adding and subtracting numbers is the same process for all of those. Now, where we start getting into a little bit of a problem is data representation of negative numbers. This becomes how do we do this in binary? So if we want the number -5 in decimal, what do we do? Put a little dash next to it as a -5, right? I mean, it's meant to be funny, and it's also meant to be true. As human beings, we look at that, and it's immediately obvious to us that it's a -5, because we know how to read that. But when we're dealing with a computer and all our values are represented in binary, how do we represent that negative? Kind of see what I'm getting at here? Well, so if we think about kind of the history of it, we can look at a couple different approaches to it. We can decide that we're just going to use one of the bits for positive or negative. So, and the one thing I want to maybe emphasize here is, whenever you're doing this stuff, look at it through the lens of how we evolved our architecture to where it is today. I mean, we didn't just have our computing architecture that we have today day one. We've evolved to that, and we've taken some weird turns and wrong turns and right turns and things like that. But at the end of the day, we've had to make some guesses. We've had to say, well, why don't we? So if we go back to the beginning, wouldn't we say that, all right, I have 8 bits to work with here for representing numbers. So let's go way back to like EDVAC and UNIVAC, the big gym-sized computers where we had vacuum tubes that were like light bulbs, right? Turning them on, turning them off. You know, those were our bits. Our zeros and ones were these giant light bulbs. So to represent a negative number, we could use, if we were dealing with 8-bit registers, so 8-bit number, we can use one of the bits, one of the light bulbs. Maybe if it's on, it's positive. If it's off, it's negative. Something like that. We can decide that we're going to utilize 1/8 of our data for representing sign. Could do that, right? In fact, that's probably what we did. It's the most obvious approach, isn't it? We didn't have to come up with any sort of weird mathy thing to make it work. It's just like, oh, well, we just give up a little bit of data, and now we use one of the bits. Okay. In fact, when we talk about Java and the different data sizes, a 16-bit 16-bit signed number. What does it mean to be a signed number versus an unsigned number? If I say a number is a 16-bit signed integer, what does that mean as opposed to a 16-bit unsigned integer?
Unsigned is the regular number in format of binary. Signed is the first precision goes to the positive or negative. Am I in the right?
Okay, so that sounds like a really complicated way of explaining something pretty easy.
Okay.
Isn't it basically just one of the bits is dedicated to saying positive or negative?
Well, that's kind of what he said.
Yeah.
So what's the difference between a signed number and an unsigned number?
Signed, you have a negative bit.
Yeah, signed could be negative numbers. Unsigned doesn't have negative numbers. All right, so if we have a 16-bit signed number, we're using some aspect of it for holding the negative value. However, we're going to do that. So the implication is that signed number, being 16 bits, can hold a larger maximum value capacity than, or in terms of biggest positive number, than an unsigned equivalent, because we're having to somehow make room for the sign, the negative value. All right. So if we're talking about in Java, a 16-bit signed integer would be a short in Java. So that can hold values negative 32,768 to positive 32,767, which is plus or minus 2 to the 15th power, because one of the bits is used for sign. Make sense? If we have a 16-bit unsigned number, what's a 16-bit unsigned value in Java? What primitive type is that? Or C, or C++, or C#, or Swift, or Objective-C. So the answer is the same for all of those. What's a 16-bit unsigned? Actually, technically in C, it would be an 8-bit unsigned, but Maybe it should give you a hint, but it looks, I'm not gathering that it did. 16-bit unsigned is a char. Okay, because it maps to the Unicode character set. In C, it was an 8-bit unsigned because it mapped to the ASCII character set, which was 0 to 255. Unicode is 0 to 65,535, which is the absolute value of negative 32,768 plus 32,767. You get the 0 to 65,535.
Because we added more symbols.
Well, yeah, when we went from ASCII to Unicode, yes. But, you know, an unsigned 16-bit number can hold a smallest value of negative 32,768 to a maximum number of 32,767, positive. Whereas an unsigned 16-bit value can hold, smallest value is a 0, because we don't have to deal with negative. But we get the full capacity of the 16 bits. So it's 0 up to 65,535, which, how do you get the 65,535? You take the absolute value of negative 32,768 and add to it positive 32,767. Makes sense? That will give you 65,535.
It's a lot of numbers, but sure.
Isn't it just 2 to the 16th?
2 to the 16th. Yep. 0 to 2 to the 16th. Well, actually, it's 0 to 2 to the 16th minus 1. 2 to the 16th is the maximum total number of values, which is 65,536. That's the max. That's the number of uniquely identifiable characters in the Unicode character set. You don't have these numbers memorized?
Are they all assigned?
I don't. The short answer is I don't know. It would surprise me if they are. ASCII is not.
Unicode is, you don't think they are?
Say this again.
You don't think they are?
It would really surprise me. That's a lot of unique characters.
I mean, wouldn't it make more sense to have it assigned to keep a consistency between them?
Oh, no. So, but understand the purpose of Unicode. The purpose of Unicode was that ASCII, which only had 256 unique characters, didn't cover alphabets from all over the world. Really only covered English and our punctuation and then some smiley faces and cards and stuff like that. It didn't handle foreign languages. Well, so if we say that in the computing world, I mean, I'm just making up a number, but let's say that in the computing world, realistically, we probably represent 20 foreign languages. I mean, that might be far off, but it doesn't necessarily feel like it's that wrong to me. I mean, there's zillions of languages in like sub-Saharan Africa and stuff like that probably are not really.
A lot of times they're Romanized, though.
Oh, whatever.
Is that what you're saying?
Well, I mean, my point is that chances are what's in the current Unicode character set is representative of the languages that are likely to be represented in the computing world. If there's a keyboard that might have those characters on it, it's probably in Unicode. You know, but even though there's languages in sub-Saharan Africa that are made up of clicks and stuff like that, they're not technology users in general. You know, so I mean, it's stereotypical, but chances are they haven't been assigned a Unicode spot
They haven't
yet.
made keyboards for them.
But what's the purpose of Unicode? The purpose of Unicode is to take us from the limited 256 unique characters of ASCII and move us to the less limited 65,536 unique characters of Unicode. Make sense?
Yeah.
Well, was there any room in between? That's a computer organization architecture question. Why did we make the jump from 256 to 65,536?
By the time we made the switch, we needed them all.
But we just said that we probably aren't using all of them now. I'm speculating that's true. I don't necessarily know that's true.
The Unicode 9.0 has 128,237.
Characters?
Yeah.
Okay, so it must be a...
So you
There's a couple different planes, each with that number.
okay? So you're
So it almost deals with like an XYZ type thing?
Yeah.
So what you're okay? I think we're misunderstanding what the question that we were covering was, because I thought you meant that like the assignments of the bytes were dynamic for what they represented.
Well, no, they're hard-coded.
Okay, that's why I was really confused. I'm like, why would
Yeah, like an A.
Okay,
And A will be this value.
But what you were talking about was that we aren't using all bajillion of those bytes to represent something currently. Is that what you're saying?
Well, what I'm saying is that it seems likely to me in Unicode. So forget about the Unicode 9.0 thing. So let's just talk about your version 1 Unicode. So in Unicode, we can uniquely differentiate 65,536 unique characters.
But we simply aren't using all of them.
Yeah.
Okay. Okay.
Think of it just like IP addresses.
Right.
So the whole reason we're going from IPv4 to IPv6 is because we're out of IP addresses, right? You know, because IP addresses are an 8-bit number followed by a dot, followed by an 8-bit number, followed by a dot, followed by an 8-bit number, followed by a dot, followed by an 8-bit number, followed by, no more dots. We're done with dots. Those are unsigned numbers, so 0 to 255 in each of those.
Yeah, we were covering different questions.
Yeah, I got it. So we're running out of those. That's why we're moving to IPv6, which gives us a larger space. So my question is if we started off with ASCII being 256 unique characters, and then we made the jump to Unicode. So, our upgrade to ASCII went from 256 unique to 65,536 unique. Why?
My guess is because we wanted to add the 4 bits.
It was 8 bits. We went from 8 to 16.
Oh, probably to keep that consistent. 2 bytes.
So if we just think about this in terms of computing stuff, how often do you suspect we have a 12-bit register? Does 12 bits sound like a thing to us? In any of your computer science education, have you run into a situation where, oh yeah, such and such is an unsigned 12-bit value? 12 doesn't sound like a familiar thing because it's not a power of 2. Make sense? With computers, we're typically working with powers of 2. We'll see in here that octal and hexadecimal also play a role, but it's not because of the power of 16 or the power of 8 thing. It's because of how binary can easily move in between octal and hex. Yep. So you can make those transitions really easily.
So it was just because they wanted to just make it.
Your next option was to add 8 bits. That's your next power of 2. Right? So we went from 8 to 16. 16 gives us a whole lot more storage. From 16 we went to 32. And,
objectively, we probably won't use all that.
well, we can always say that, but we have more languages, or we come up with new ways of representing stuff that aren't even spoken languages. Who knows? Yeah,
Aliens show up.
Yeah, aliens show up. We have to take their languages into consideration.
Gotta add Klingon.
Klingon. Actually,
Is that part of
you can
Unicode?
confirm this, but I think Klingon is in Unicode.
I wouldn't doubt it.
I really think it is.
Klingon's in there. No. Unicode proposal made in 1997, formally rejected in 2001. They tried. That's the point.
All right.
Let's see what else. I wonder what else.
Well, so hold on. Let's keep going. We only got this 4 more minutes. I just want to get through the two's complement stuff. All right. So point is that we need a way of representing negative numbers in binary. Okay. So the idea here is that we've talked about a straightforward way of just taking away part of our value, right, and storing it in the in one of the bits. And the reality is that is what we ultimately do, but it's not as straightforward as that. We just don't take the far left bit and say, oh, this is either a positive or a negative value. Like I mentioned a little bit ago with vacuum tubes, we don't just take that last light bulb and decide this is positive or negative. It's not the way it works. Instead, we have to convert our value into something else. All right? So we have something called the 1's complement and the 2's complement. All right? So these guys are modifications of an existing binary value. We might say that we're encoding it for a certain purpose. Make sense? So our paper is going to deal with, so here I'll even write it. Write a 2 to 3 page paper discussing the role of 1s and 2s complements in binary numbers. Why do we need them? And how are they each used? All right, so what you'll be looking at is effectively how do we encode binary numbers so that they're, again, we're coming back to like this idea of staging, so that the number is staged in preparation for something else. All right, so I'll give a quick little punchline of this, like for 2's complement. What you do is instead of for like subtraction, for example, so forget about negative numbers for a second. To implement subtraction, what we actually do is you take the 2's complement of the second number and then do add, do addition. All right, so it's adding a positive number to its negative to the negative number instead of subtracting this number from this number. All right, so so kind of go through that, learn about how 1's complement, 2's complement works. We'll start off next time talking about that. Here, let me copy this here real quick. So I'll just go ahead and put this into the system. And then, like I said, your reading assignment will be 2.1 through 2.3. And then exercises, so then the actual homework assignment will be exercises 2.1 through 2.7, which and keep in mind there's like 40 some exercises here, so that's a very small percentage of all the exercises. So it's not like, I thought you said you were giving me less. Those are smaller. I looked through them. All right.
Okay.
Promise you those will be more palatable. Sound good?
Yeah. It wasn't actually in like the official Unicode that they tried to get it